continue with the concept of torque. Now, if you see this diagram, you see that this is a door. If you look from the top view, this is the hinge, or you can call this the pivot. Now you apply a force. If you apply FA, we say we take the distance from here, let's call this dA, times FA. You will get torque. Okay, dA multiplied with FA. Now, if you notice something, you will see that FA and dA are making 90 degrees, right? So we can say that torque is distance times force that is perpendicular to the distance. So what if we would like to use FC instead? Yeah, you can use FC if you want, but then you won't be able to use this dA or RA. You will have to change to this RC. Okay, so you need to know the value here, which is going to be perpendicular to the line of action force of FC. So in this case, it will be torque equals FC times RC. So this is torque C. This is torque A, right? So there are different cases or different scenario. So you can see here that the term torque here, we use R that is perpendicular to F, or we can say torque is F that is perpendicular to R. Either way is fine, but they have to be perpendicular to each other, the two quantities. Yeah, you can see here even. Same. So this and this is actually the same equation. What happened if we look at this case and we were given only this F and this R? Okay, if you're given the angles, okay, you want to make sure that these are the two values you want to use, R and F perpendicular. So I want this and this. So both of them will be making 90 degree. If you notice here, this and this. See? So torque in this case is R multiplied by the F perpendicular here is F sine, right, theta. Then you can say, okay, this is F sine theta. Okay, so this is torque. This F here is useless, the parallel F. When you say F double dash, it's a parallel F. So we don't use this one. Okay, all right, let's see an example here. So this example is talking about bicep. The bicep muscles exerts a vertical force on the lower arm. Okay, this is the bicep. Okay, so you are exerting a force to the lower arm, and there's the axis here. You can see the distance here and the force that you exert to lift an object, right? So the rotational axis is on the elbow joint, which has the distance 5 cm, right, from the muscles. So the question is, they're asking you to find the force according to the torque according to this force. So torque equals F times D, perpendicular distance. So I have to convert this cm into meters. So convert that and multiply the two quantities out. You will get 35 Newton meters. So this is the value for torque exerted to lift the object with your hands. Okay, now let's see if there is an angle created. So there's an angle created if you bend your arm down 30 degree from horizontal. So what is the value of the torque produced now? Okay, so that is easy. You can now say that. Let's look at R. So the R here is 5 cm, right? So we are looking at it, we are saying that, okay, let's break it into, if you take this, it will be cos of 30, right? But if you take that, it will be sine of 60. So you can take this if you want. So you're, in this case, they're saying that this is the distance we want, the perpendicular distance, which is going to make 90 degree. So this is the value I'm looking for. If I know this is 5 and I want to find that, I will do sine of 60 to get this. So sine of 60 will get me this value here. sine 60, 0.5, 0.05 times sine 60, okay, times the force applied here. So you get 30 Newton meters, okay? All right, moving on. So this is now, if you recall the equation, alpha. What is alpha? So first, let's go with omega. Omega is change in angle, right, over change in time, or 2 pi f. But if you're looking at alpha, it is omega, change in omega over change in time, right? Or A, acceleration is equals to alpha times r. Okay, this is linear. So when you're looking at torque, we're saying that alpha is directly proportional. Okay, let me write alpha like this. And this is the proportional sign, is proportional to the sum of torque. Okay, if you recall, F equals ma. I can change this a. I can say m times alpha r. Okay, makes sense. Now let's put this force in here. So change this, torque equals Rf. Change this to mr alpha. If you simplify, you're getting torque equals mr square alpha. There's another term I want you to remember. This is called moment of inertia. This is called moment of inertia. It's I, denoted as I. I is mr square. So moment of inertia is the quantity that represents the rotational inertia of a particle. Okay, so this depend on mass and radius. Keep that in mind. Okay, so torque just now was m r square alpha. Now I'm going to change this to I. See, so another equation for torque is I alpha. See this, right? What if you have so many mass and so many different radiuses? So you can take the summation of that to find the total moment of inertia, or we call this rotational inertia. So what is rotational inertia? Just imagine these two and you spin it. So if you're spinning this, right, which one will have more moment of inertia? Let's say if both have the same mass, if both of them have the same mass, then this guy with greater R, right, R2, and this is R1. So if R2 is greater than R1, and let's say M2 is equals to M1, then I2 will be greater than I1. Just remember that. Yeah? All right, let's see an example here. So this is talking about two weight on the bar. So these are the two weights on the bar. Okay, now they have a different eye. Let's look at the question. It says two small weight of mass 5 kg and 7 kg are mounted 4 meters apart on a light rod whose mass can be ignored. Calculate the moment of inertia of the system when rotated about the axis halfway between the weight. So this is the axis of rotation, right? So what do? I just need to do this. Take the distance from the rotational axis. This is 2 meters. Square this. This is the R, right? So R1. And this is my R2, also 2 meters. R2. So square this times with that. See? So first value here, which is 5 times 2 square. Second value, 7 times 2 square. Add them, the summation, to find moment of inertia. So if I add this, I'm getting 48 kg meters square. So this is the moment of inertia. Okay, let's see the second scenario. The second case, when rotated about 0.5 meters to the left of the 5 kg mass. There you go. Now this time you move the axis of rotation here. All right, so this is my R1, right? And this is my M1. Now where's my R2? R2 will be from this to this, and this is my M2. So R2 is equals to 4.5 meters. Okay, so simplify it again. This is 5 times 0.5 square plus 7 times 4.5 square here. add them, you can see that you're getting more moment of inertia, right? Comparing this. So I can just call this IA and this IB. See that IB is a lot bigger than IA, right? The moment of inertia is different because the axis of rotation is different. All right. So this is an equation. Different object, okay, different type of figures may have different equation for I. So this is a thin hoop. This is a thin hoop with thickness. So if there's a thickness involved, then we take that equation. So this is like half mr squared plus 1 over 12 m, the width square. Okay. If it is a thick solid cylinder, there you go. If it is a hollow cylinder, this one, right? So this is a different I for different scenario. If it's a sphere, 2 over 5 mr squared, right? You can see all this. So depending on the cases, we use the equation depending on that.